So welcome back, everybody, and welcome to a new week. And the topic this week is a continuation of the introduction of second quantization, which we discussed last week. And we are going to look at operators in second quantization and diagrammatic representation, and we're going to look at Wick's theorem, which is going to simplify the calculations of expectation values and transition probabilities. Now, one of the things I'm going to do today is actually in a very, very boring way to go through all the actions of the anti-commutation operators so that we can compute expected values. And what you're going to see then is that this is very cumbersome and not very efficient. But when doing this, you will see some patterns. And these patterns are going to motivate the introduction of Wick's theorem, which is used in quantum field theory, in many-body physics, and it's a compact way of calculating expectation values. And you can, if you want to, you can easily program Wick's theorem. So if you have a chain of operators, you can easily then find what are the relevant expectation contributions to a specific expectation value. Just to give you some quick messages, you probably saw that from the mail which I sent in the beginning of the week, and that's also a mail which contains reading suggestions. A lot of the material is covered by this textbook by Sabo and Östlund. Many of the textbooks are a little bit sloppy with the derivation of Wick's theorem, so we're going to spend some time with actually deriving it. So many textbooks simply just state it and then they use it. Now, the Jupyter book is contained here, so I'm gradually updating this, and this is going to be a kind of a more in-depth collection compared to the weekly slides. So you will find the Jupyter book, which is a searchable document, which then is going to contain everything plus much more, and it's going to contain much of the same material which you see in the weekly slides. So you can use that one as a kind of reference for what we will cover this semester. But you will also find, like if you look at the schedule here, you will typically also find some reading suggestions. And you will find typically chapter 3.1 or chapter 3 of Shavit and Bartlett, and you have access to this textbook in this folder on literature. This is actually a pretty good textbook, and it's very much used in the field of quantum chemistry, which is essentially applied atomic physics and molecular physics. Then we have the exercise sets, as you've seen. And if you also go into this folder with the exercises, you will find a solution to the exercises. So if you then click on the exercises here for 2022, you will then find answers to the week 35. And if you want to use a text file and use them as a kind of background for your own editing of the exercises, feel free to use these LaTeX files, if you're familiar with LaTeX as a mathematical typesetting program. Any questions about practicalities? So I will always post the answer to the exercises so you can look them up again, and if you didn't have time to go through the exercises, you can always look them up here. Now, what I want to do now is to repeat a little bit of what we did last week, and then look at some examples. And when I'm going to derive the expression for the different operators in second quantization, this is a kind of a boring repeat of using the spectral resolution of an operator. And then I'm going to use the slides. But then for many of the examples, I will switch between the slides and the whiteboard. So what we did last week was to introduce these operators. And what we have done is to represent a state function now in what is normally called a second quantized representation, or the number representation, or people normally used to call this in Fock space. And that is an abstract space where we have now projected out the spatial degrees of freedom. So that means that a state is now simply given by the specific quantum numbers and how many particles occupy that specific single particle state. So keep in mind again that the way we construct a many-body wave function now is by assuming that a single particle picture is a useful approximation to a many-body wave function. It may not be the case. So there's nothing, which guarantees that this is a viable approach. And typically, if you have a strongly interacting system, then this kind of single particle degrees of freedom, which you use to construct a many-body ansatz, is something which will normally break down. So this ansatz is viable if you have normally what you would call weakly interacting systems, or systems where still a single particle picture makes sense. We are coming back to this again and again during this course. And the different many-body methods, what they typically do is that they use this many-body basis of solutions of a part of your Hamiltonian problem as a way to build up correlations in terms of that basis. So it's a way to interpret nature, which may not be the way nature looks like. So if somebody gives you the exact wave function, that could be very different from the ansatz you make. Whatever the exact wave function is, by the way. Okay, so what we did now was to then introduce this compact notation. So we have so this is actually a vector, this alpha. It can be a vector, or it can just be one single state here. And then we don't need to represent that with a vector. And then the compact notation is that we would have a many-body state. This AS is anti-symmetrized, so this is for fermions. And then the state which we then build up is a state where we now have filled in with the different single particle states. So that means that we have these creation operators. And then we would have a new state like this. And normally we would like to reshuffle it so that we have a specific ordering. And normally what we choose is an ordering of these single particle states in a kind of ascending order, which often follows the ordering of the single particle energies. But this is a table you would make when you're setting up a many-body problem. And then you have the Hermitian conjugate. And what we derived last time was actually the anti-commutation rules. So we have, for the same operators, here they are equal to 0. And then we have the case with the anti-commutation rules, or anti-commutator, where we have a creation and annihilation operator. So these are the rules which we used last week to calculate expectation values or transition probabilities. Now, one of the operators which we introduced last time was something which we called the number operator. And this was basically where we ended the lecture last week. And we looked at this operator, and we found that it actually conserved the number of particles. So what we're going to do a little bit later, after some few examples today, is now to move on and look at the way we could represent the one-body operator. So this does not need to be the one-body operator for the energy, but that means it contains kinetic energy and an eventual external potential, but it could be any one-body operator. But we are coming back to that. So what I'm going to do now is simply to switch back to the whiteboard, and we are going to take a look at the applications of these creation and annihilation operators to the calculations of properties of the number operator. So let's look at some examples, and we're going to follow up again with the number operators. So if we now look at a specific example here with the number operator, and we define this number operator as simply the sum over all the states which we have, which are now filled with a particle, and then we have some A of I dagger A of I, like this. So sometimes I'm going to put a subscript alpha 1, alpha 2, and so on. In other cases, I'm just going to use a subscript I. As you can easily see from the context that this refers to a set of quantum numbers which the single particle states can have, or the single particles can have. So one thing which is nice with this operator is that this operator is what we call idempotent. So that means that if I square it, this is actually equal to the operator itself. And just to see that, let's now pick one of these. So let's now pick, so hats on top of a variable. That means that this is an operator. So I'm trying to keep that kind of notation. So let's look at one specific term here. And you can easily see now when we use the anti-commutation rules that this is actually the case. So if I now square it, so this is the same operator. So this is going to be AI dagger AI multiplied with AI dagger AOI. So again, these states, we have assumed that these states are normalized and orthogonal. So that means that they are orthonormal, as we usually call them. And then when we now act with this operator, so normally this is something which always confuses people in the beginning. When you see something like this, we are always thinking of this acting on a specific state. So everything we do now is this operator acting on the vacuum state. So when you see a commutator, it's always this set of operators acting on something, but you skip that notation, you skip the state which it acts on. So, but that is implicit that these actually do perform some actions. So if you now look at this, what we can do now is simply to use the anti-commutation rules. So we would now take these two here and match them so that we have the creation operators to the left and the annihilation operators to the right. Because when all the annihilation operators are to the right, when they act on a vacuum state, they give automagically 0. So keep that in mind because we are going to use that when we derive Wick's theorem. So when we now use the anti-commutation rules, we can actually rewrite this. And then we obviously have 1 here. We don't need to write a Kronecker delta. And then we have AI dagger and AI here, like this. And now if this acts on a state, we have an AI here. Obviously that one has to be equal to 0. So that means that this can be then rewritten as an AI dagger of AI. So, and this is equal to the operator itself. So that's an example of an operator which is idempotent here. Now, another thing which is useful to derive with this number operator, and you will see similar relations for the other types of operators, is the following operation. So if we have Ni and j, so this is the same as if we write the commutator minus Nj of Ni. And what we are going to assume now is that these are different operators because if I and j are the same, this obviously has to be equal to 0. So the assumption we're going to do now is that I is different from j. So we're just looking at 2 contributions of the number operators. And I'm putting the subscript to indicate that now it's a specific state which it is acting upon. So if I do that, what I will have then is, so let's put this in parentheses. So this will be an AI of AI, and then I have an AJ dagger AJ minus AJ times AI dagger of AI. And then we can use the anti-commutation rules here and just reshuffle the operators. So I'm going to leave this one as it stands, and I'm simply going to reorder this one so that this one becomes equal to the other one. And then you will see that the first thing I can do now is actually to take these 2 operators and shift them because I want to get the AIs to the left and the AJs to the right. So I'm gradually going to do that. So let's just put a sign like this under here. And then we're going to get an AJ dagger. And then we have an AJ. We have a delta IJ, and they are different. So that this has to be equal to 0. And then I have minus, and then I have an AI dagger, and then this is multiplied with an, this is then multiplied with an AJ, and then I have an AI here. Then I know the first term is equal to 0. So this becomes equal to minus, and then I have a minus, so that becomes a plus here. So then I have an AJ dagger, and then I have an AI, and then I have an AJ, and then an AI. Now I can reorder. I can use the anti-commutation rules for AJ AI, and then I can use the same for AJ AI. So this is the same as plus, and now I have an AI dagger, AJ dagger, and then I have an AI and AJ. So each one of these combinations, because what I'm doing here, I'm simply using, if you look at these expressions, here I'm using the anti-commutation with AJ and AI, which is equal to 0. And here I simply just used AJ dagger of AI, which is also equal to 0. And then, if you look at this final term, I have plus, and now I'm getting a plus, and then I'm going to change these two here, just to switch them and use the anti-commutation relations again. So I'm going to get a delta ij, which is obviously equal to 0, because we have assumed that they are different, because else it would have been fulfilled immediately. And then I have an AI of aj dagger, and then multiplied with aj. And this is the term we started with here, which we have left untouched. And then we have an AI, AJ dagger, AJ, and we see that this is exactly equal to 0. So that means that these two operators, they commute. So when I say anti-commute, then I have the anti-commutation relation. And then when I say commute, then I have the standard commutation relation. So in some textbooks, you will see notations like this. If you take two operators, A and B, you will see a minus sign here, and then people indicate this operation, minus B times A. Or you will see a notation here, we have a plus sign. And then the definition of that one is equal to B times A here. We are going to use this standard notation. So when I write AB, this is the kind of notation I will follow. And sometimes it happens that I forget to put on hats here. And then I'm going to have this notation for the anti-commutator. And that's given by AB plus B of A. So this just, so you see the kind of notations, because in some textbooks you will see the other notation being used. Okay, another example, just to bring that up, is another commutation relation. And that is also something which is very useful. And this is the relation between an AI dagger, and then I have an NJ here. And this is the number operator. And I'm not specifying now whether I is equal to J. So I'm just leaving that open, okay? So if we take that one, this would be the same as AI multiplied with AJ of AJ minus AJ dagger AJ times AI dagger. And keep in mind that this is always acting on some kind of state. So now what I'm going to do is since I'm going to act on a specific state, I always want to reshuffle things so that I have an annihilation operator which acts on the vacuum state to the right, because then I know that this is automatically equal to 0 if it acts on the vacuum state. So if I now do the same exercise again, so I'm just going to leave, so I can actually change my AJ with AI, and then I can rechange here thing, but let's just rewrite it now a little bit. So we can rewrite this one as an AI, AJ dagger, AJ, and now I'm going to shuffle around here. So I'm going to have an AJ dagger, and then I'm going to have a delta IJ minus AI dagger times AJ, like this. Does that sound okay? So what we get then, and now remember also that this term, delta IJ, is actually a vacuum expectation value. So we wrote this last week as IJ, and what it stands for is actually 0, and then I have AJ, AJ, and AI acting on 0 here. Let me just write this one a little bit better, because it wasn't, let me just put it down here. Didn't. So this quantity which you have here is actually given by 0, and then I have an AI, and I have an AJ dagger, 0, and this is the same as IJ here. So in this second quantization, representation of Fock space as we call it, this represents actually this expectation value, or you could call it, is actually the norm of the two states which we have, which we are dealing with here. So that means that if I now look at the last term, this is a term which so I can actually rewrite this as an AI, AJ, AJ, and then I have a plus an AJ, AI dagger, AJ, minus AJ dagger, delta IJ. Now, if you look at this term here, what I can do now is to switch the two creation operators. So this becomes minus. So I'm going to get an AI, AJ plus, AJ minus, AI, AJ dagger, and then I have AI dagger. And, oh, sorry, not that one. I was a little bit rushed here. AJ. And this is now given by minus AI times this delta IJ. So whether I put a J or I there doesn't matter on the last one, because there is a Kronecker delta IJ. Okay, so these two first terms, you can see they cancel each other. So what you're left with is minus AI dagger delta IJ. And when this now acts on a vacuum state, you're actually creating now a state in the single particle slot I. If these are fermions. If they're bosons, it would be a boson in a single particle slot I. You can do the same thing with AI, and I'm just giving you the answer here. So if you take these relations, what you're going to get then is a delta IJ multiplied with A of I. Now it depends on what you're acting on. So if you're acting on a true vacuum, this is automatically 0. If you're acting on a state which is occupied in the state I, then this is going to annihilate that state and bring you back to the vacuum state. But these are relations which are very useful to actually see, because they can be used later when you're dealing with the calculations of excited states in some theories. And there's something which is called the equation of motion method, which is actually based on these type of relations between commutators. Now, the thing which I wanted to do now, before we move on, is actually to go through an additional example. And I'm simply going to state now the form of a one-body operator. And then I'm going to run the calculations of an expected value. And then with that, we are going to go back to the slides, and we're going to derive the second quantized expression for a one-body operator. So let's simply state the expression for a one-body operator. And in this particular case, I'm going to look at the one-body operator for the energy. So this could now contain the kinetic energy. It could contain an external potential. And you remember that what we did now was to sum over the number of particles. And then we had this operator here, where we now had the general coordinates. So this could include the spatial degrees of freedom, but it could also include the spin degrees of freedom. So we just leave that unspecified, what these x's represent. And what we had in what is normally called first quantization, we would have this operator acting on a state, alpha, and then we had an eigenstate, alpha, multiplied with an eigenvalue, multiplied with the eigenstate here. And we could then define a matrix element. So let me just quickly remind you of these quantities of H0, which was given by delta alpha beta. So we are assuming now that this is a basis, an orthonormal basis, and these are an eigenbasis of the operator H0. And this is the same as the integral over dx, and then we had a phi alpha complex conjugate of x, H0 of x acting on phi beta of x. So we are just going to assume that this is the operator. So in a certain sense, it's not a general one-body operator, which defines a one-body type of many-body operator. So when you look at the definition which you have here, this is a one-body operator, and this becomes a many-body operator, but still it acts only on one particle at a time. So you're looking at the kinetic energy of particle 1, particle 2, and so on. So the energy in general is an additive quantity. In the literature, you will see this being called an extensive quantity. So that means that the energy is normally something which depends on the number of particles. If you think of a quantity like pressure or temperature, that is normally called an intensive quantity. And all the objects in a system, they feel the same pressure. So the energy is in general an additive quantity. Now, what I'm going to do now is simply to state the shape of, or the mathematical form for this operator in second quantization. So a general, yeah?
Why is the expectation value and Kronecker delta? Is it shouldn't it be multiplied by the epsilon beta?
Oh, sorry, you're right. So this should actually be an epsilon alpha here, sorry. Sorry, I forgot the epsilon alpha.
Alpha or beta?
It's because if you look at this expression here, when this one acts on that, then let me just take that one out. When this one acts there, what you get then is a dx phi alpha complex conjugate multiplied with epsilon beta phi beta of x. And then we have assumed that this is an orthonormal basis. So that means since this is just a constant now, this becomes equal to delta alpha beta times epsilon beta, which is then just epsilon alpha.
Okay, so
yeah, just guys, feel free to interrupt here in case something is unclear. Good. So with that definition, what I'm going to state now, without having shown it, and we are going to show that a little bit later, is that in second quantization, or in this number representation, this operator can now be written. So we have this H0, and then I have a general sum over alpha and beta. I have this matrix element, which we defined here, of beta, multiplied with A alpha dagger, A beta. Now, in the special case which we looked at here, this reduces to a single sum because we now assume that these states, beta and alpha, are eigenstates of H0. So that means that I have a Kronecker delta, so this reduces to a single sum. But in general, a one-body operator, when I write this in second quantization, if I now replace this H0 with some operator O, that will contain a double sum. But in this specific case, this simplifies to what we have here. So let's take this simplified expression and grind this through the anti-commutation relations in order to calculate an expectation value. So what we are going to do now is to calculate the expectation value of this operator with a two-body state, alpha 1, alpha 2. So we are just looking at now the expectation value. If we change the left-hand side, so if they differ by some kind of single particle states, we are looking at the transition probability or the likelihood when going from one state to another state given this operation. So in our case, this is now, if we now write this out in second quantization, this is going to be given by a sum over alpha, and then I have this expectation value of the one-body operator, and then I'm plugging in the representation of the Slater determinant in second quantization. So I have an alpha 1, and then I have an A alpha dagger, A alpha, and then I'm going to have an A alpha 1 dagger, A alpha 2 dagger of 0. Now, you know the answer here. So this is actually going to be a sum over all the epsilon alphas. So let's prove that this is the case. And in our case, the epsilon alphas are alpha 1 and alpha 2. So what we're going to show now is that this is going to be a sum over alpha I, and then I'm going to have an epsilon alpha I. So we're going to get epsilon alpha 1 plus epsilon alpha 2. That's what we're going to get. And we found that when we wrote the full Slater determinant in first quantization. So let's now repeat this exercise in second quantization. And as I said, everything we do now is going to serve as a motivation for introducing Wick's theorem. Because when I do what I'm going to do now with the anti-commutation rules is not very elegant.
It's going to be easier than the first quantization,
yeah.
But not that better.
Yeah, yeah. And the reason why I bring this up here is that you're going to see some patterns. And these patterns are going to motivate the form of Wick's theorem, which will simplify the calculations considerably. So I hope you can see the wood for the trees when we are done with some of these examples here. Okay, so if you now look at the quantity we need to look at, so we have this A alpha 2, A alpha 1, A, sorry, sometimes it's easy to write an alpha instead of an A. So what I want to do now is to place all the creation operators to the left and the annihilation operators to the right. So the first thing I'm going to do now is simply to switch these two here. And then when I switch that one, I'm going to switch it with alpha 2 here. So I'm just going to do a repeated operations with the anti-commutation rules. So this is now going to be equal, and I'm going to leave out the zeros. So we're going to keep A alpha 2, A alpha 1, A alpha dagger. And now I'm going to look at the first term here. So this is going to be a delta alpha, alpha 1, minus an A alpha 1 dagger, A alpha. And this is acting on A alpha 2 dagger. So the first term which we have gives us simply a delta alpha, alpha 1, and now I have an A alpha 2 dagger. So let's just write out the first term here. So I have an A alpha 1, A alpha dagger, and then A alpha 2 dagger, and then I have a delta alpha, alpha 1, which means that what I have here is just an alpha 1, right? And alpha 1, because now I have this quantity here. So that means that this quantity here now is something which I can simplify further very easily. So what I could do now is simply, since these two here, that will give me 1 minus delta alpha minus the operators, and then I can swap alpha 1 with alpha 2, and they have a Kronecker delta which is equal to 0. So keep in mind now that alpha 1 is not the same as alpha 2, right? But let's now just elaborate a little bit more. So we have a second term. So we have a minus, and then we have an A alpha 2, A alpha 1, A alpha dagger, and now I'm getting an A alpha 1, A alpha, and then I have an A alpha 2 dagger, like this. So that's the second term. So let's now look at the first term first. So this is going to be equal to A alpha 2, and then I have a 1 minus A alpha 1 dagger, A alpha 2, multiplied with A alpha 2. I'm leaving out the Kronecker delta, if that's okay with you guys, okay? Because I have used the Kronecker delta now to simplify one of the expressions here. Then, if you look at the next term, I'm going to rewrite that one as an A alpha 2, A alpha 1, A alpha dagger, A alpha 1, and now I'm going to have a delta alpha, alpha 2 here, minus an A alpha 2 dagger of A alpha. So keep in mind now that these states are, or these set of operators are acting on the vacuum state. And then you see that the last term which we have here, this term here, is going to give me 0. So we can just leave it out now. Then, if I look at the first term, and then the second term which is non-zero, what we're going to have then, when we now manipulate these expressions further, is the following. So I can now, I did something wrong here. This should actually be, so it's easy to get lost in this sea of indices here. That should be a 1. So what I'm going to do next now with this term, I have an A alpha 2 here, and this has an A alpha 2 dagger. I have a 1 here, and then I have a minus, an A alpha 2, A alpha 1, times A alpha 1, times A alpha 2 here. Now I can interchange these two here, and I can do the same with the alpha 2 dagger and alpha 1, because these are different states. So that means that this one becomes simply minus A alpha 1 of A alpha 2 here. I can swap that one, so that gives me another minus, because I use the anti-commutation rules, and alpha 1 and alpha 2 are different, so the Kronecker delta is equal to 0. So this becomes a plus, but then I have a minus sign in front here, minus minus, because now I'm changing this alpha 2 here and A alpha 1, like that. So that gives me a plus, but then I have a minus sign in front here. So this comes with a minus. So let's still do these terms here before we jump into the last term. So let's just write, just for the sake of completeness, the last term, A alpha 1, and then I have A alpha 2 now, since I have a Kronecker delta of A alpha 1 dagger, like this. Okay?
What was the last step?
Say it again?
What was the last step? I didn't follow the last step.
No, the last term, this one, is 0, because this is acting on the vacuum state.
Just the last step, what did you do?
So the last step, I actually took this term here, and I used that alpha is equal to alpha 2,
okay.
so I just put in alpha 2 in here. There's a lot of bookkeeping, and I'm doing this simply to ramp up the motivation for Wick's theorem. Because when you've gone through this once or twice, you're going to hate it. And you're going to do this in the exercises tomorrow, but with Wick's theorem, this actually pops out automatically in a much, much simpler way. So I hope you can forgive me for going through this kind of not too exciting exercise, but it serves as a kind of motivation. And also the other thing is that you will start seeing some patterns. And this is a pattern which will simplify the calculation and the introduction of Wick's theorem. So if you now look at what we have here, So if we take this second term here, what we can do now, since alpha 2 and alpha 1 are they anti-commute, and alpha 1 is different from alpha 2, then I can simply switch the operators here, and then we are going to end up, if we now look again at what we have, so if you take this term here, so that is going to give us a 1, or actually Kronecker delta alpha 2 minus a alpha 2 dagger of a alpha 2. That's the first term. And then when we look at the next term here, I can now, I have my alpha 2 and alpha 1 here, and then I have the alpha 1 here. So what I'm going to do now, I'm going to swap, oh sorry, this is, I actually confused myself a little bit. Let me just change this a little bit, because I want to have the annihilation operators to the left. So what I would need to do is actually to swap this one to that place, and then I want this one to that place. So since I'm going to do this 2 times, I get minus, and then I have an a alpha 1 dagger, a alpha 2 here, and then I have an a alpha 2 dagger times an a alpha 1. And then I use the Kronecker deltas here. So I'm going to get a minus, and then I have an a alpha 1 dagger, and then I have a Kronecker delta alpha 2 minus, and then I have an a alpha 2 dagger multiplied with a alpha 2, and this is multiplied with a alpha 1, like that. And then what I can do next now is actually to repeat this same exercise with the quantity which you see here by simply swapping this set of operators. So these two guys, they have a Kronecker delta which is 0. So when I do the same exercise as I did here, in order to change these operators, what I'm going to get at the end here, so I'm going to have, this term gives me now 0, because I'm acting with a anti-commutation, with a annihilation operators on a true vacuum, so that gives me 0. If I look at this term and that term, so this term multiplied with that one is also going to give me 0. And if I look at the second term, which is this one, multiplied with that and that, that's also going to give me 0. So at the moment, the only term which survives from these two here is actually this term here. So when I now do the same operations here with that specific operator, when I now change it so that I can put all the annihilation operators to the right and the creation operators to the left, this final term is going to give me just one term which is different from 0. So there's going to be a delta alpha 1 alpha 1. And you can easily see that, because if you look at the exercise which I did here, this one, this set of operators is not so different from that one. So what I'm going to do first, I change these two, and then I get a alpha 2 here. Then I change alpha 2 with that one, and then I continue till I have alpha 1 to the other side. And when you collect all the things here, you will have a contribution from alpha 1 and alpha 2 only. And that means that alpha, which we put up here, this alpha, is in one case equal to alpha 1, and in the other case equal to alpha 2. So that means that when I collect everything, it means that my expectation value here, when I collect everything, the expectation value of the operator of alpha, H0, alpha, and then I have this alpha 1, alpha 2 here with a alpha dagger, a alpha of alpha 1, alpha 2. This is simply going to be epsilon alpha 1 plus epsilon alpha 2. And this is actually one of the exercises tomorrow. So use of the creation and annihilation operators with the anti-commutation rules allows us to compute these quantities, but we have to go through all this boring shuffling of creation and annihilation operators, so that at the end we have annihilation operators acting on the vacuum to the right and the creation operators to the left, plus a series of Kronecker deltas. So this kind of pattern repeats itself, but it gets extremely complicated. And at a certain point, when you go to, let's say, a free body Slater determinant, you're just going to lose, the overview, because you will have so many indices to keep track of that at a certain point, it just becomes a very, not a very practical algorithm for finding expectation values and transition probabilities. So I'm doing everything here just to motivate the introduction of Wick's theorem, which we are going to jump into after the break. So I'm going to put the recording on pause. So what I wanted to do now is to go through the way you can derive that expression for an operator in second quantization. So what we started with in the beginning of the semester was an operator which now contained the specific degrees of freedom. It could be the spatial degrees of freedom. If you're thinking of kinetic energy, we could have a one-body operator which acts on spin. So we could think of particles moving in a magnetic field. We could think of particles moving in just an external potentials like a harmonic oscillator, or it could be the external potential which is set up by an atom or a molecule. And then we spelled out all the degrees of freedom. Now, one of the things which we can do now is to use what's normally called the spectral representation. And I assume that you have seen some of these things in a basic course in quantum mechanics. So what we are doing now is simply that we take the operation of H0 on one of these single particle states, and we can rewrite this in terms of the spectral decomposition, where we now have this alpha k prime, and then we have the matrix element, or the transition probability or expected value if they have the same states here. And these matrix elements are I normally call these matrix elements. They are elements which we can calculate based on the single particle basis which we have chosen. So if we look at this expression here, when we now add the action of this one body operator on the different states, this is going to be a sum which now contains the action of this operator on every particle, x1, x2, up to xn here. And you remember that when we did the one body operator, what happened then is that when we performed permutations beyond the ground permutations, so we permuted particle 1 and 2, 1 and 3, 1, 2, 3, 1, 2, 3, 4, and so on, all these permutations gave 0. So we are just left with one basic term, which is just the ground permutation, or no permutation at all. And then what we have to do now is simply to run through this sum of the parameters alpha k here. So we have picked up an alpha 1. So this gives us this matrix elements, and then we have the product of all these single particle wave functions. And when we now interchange particle 1 and 2, if we do that in the specific sums, we would get a sum which looks like this. And if you continue by computing all possible permutations, we can actually rewrite also the Slater determinant in its second quantized form and skip the dependence on the quantum numbers x of I. So if we sum up all these contributions and taking care of all the possible phases which can take place, then what we end up with is a set of terms which look like this. So you could now think of this now containing this term here, containing all the actions which we have on this specific determinant. So this is now a Slater determinant. And then when you add up here, and keeping in mind that these equations here can be further manipulated if you use the properties of the creation and annihilation operators, then we can rewrite every term in this sum here in terms of just this matrix element, and then we have the Slater determinant and the creation and annihilation operators. And when you do that, then you can rewrite the sum of all these terms in terms of a double sum here, and where you then have an operator now, which you will define as this H0 hat, which then contains the sum of all possibilities alpha and beta. And this is an operator which then would act in turn on this specific Slater determinant, which you see here in second quantization. So I invite you to take a look at these derivations. The important thing for us now is not to go through all these kind of small details. So just take a look at this and convince yourself that this is correct. And then you will see that we can derive the expression for the second quantized form of an operator in first quantization, which now has to look like this, based on these manipulations using the spectral representation. Now you can do that, and here you see an example which actually is close to one of the exercises we have tomorrow. Then you can repeat the same thing with a two-body operator, which is a little bit more convoluted when you do it, but it's basically the same exercise. And when you run through it, you can then show that the two-body operator is actually given in terms of this expression which you see here. So one of the kind of small homeworks for tomorrow, in addition to the exercises, is actually to convince yourself that this algebra is correct. So I hope you can forgive me for not going through this. I did it in the beginning some years ago, and I actually just spent something like close to 2 lectures on just going through all these indices. And it's just a permutation of indices and reordering of the equations. So there's nothing deeper than that into it. But the whole thing is that you're using the spectral decomposition, which we have here. And with that one, you simply rewrite these products, which you see here, in terms of a Slater determinant. And then, since you have these alpha primes, you can rewrite these quantities in terms of creation and annihilation operators. And with that, you get to the form which is the common form for a one-body operator in second quantization. And in case these states, alpha and beta, are eigenstates of H0, this reduces to a single sum. So what I'm going to do now is actually to set up these operators in second quantization and then start looking at calculation of expected values. And this will serve as a motivation for Wick's theorem. So in one of the exercises tomorrow, you will actually practice on calculations like this. But you will also see now that for one of the exercises tomorrow, you will basically find the answer to the exercise here. So I hope you don't get offended if you find solutions to the exercises in the lectures, but it's useful actually to go through them yourself. But I just added here for your own, for completeness. So in this specific case, I'm taking a two-body Slater determinant and I'm grinding through all the operations of anti-commutation relations in order to have the creation operators to the left and annihilation operators to the right. And then these terms will all give 0. And when you do that, you will find that the expected value is actually what we had before. So this is going to be one of the exercises for tomorrow. So I invite you to take a look at the slides here or the material and then just try to repeat or convince yourself that it is correct. So I wanted to focus a little bit more on the application of Wick's theorem or the derivation of Wick's theorem, because this is something which is going to simplify life considerably and allow us to calculate these expected values or transition probabilities in just one shot. So let me go back to the notebook. So what we have, in addition to the one-body operator, as long as we are dealing with a two-body interaction, is that we can write this as a one over half, and then we have a sum of all these indices. And these indices run over all the single particle states which we have. And then we have some alpha, beta, matrix elements, gamma, delta. And then we have an operator, a creation operator. And then due to the Pauli principle, this delta and gamma have actually shifted place. So it's given like this, and you can see the derivation of that in these notes on the two-body operator in second quantization. Now, one thing you can do now is to introduce this anti-symmetrized matrix element. And this is something which will compactify the calculations. So you can rewrite this. So you will often see this in two disguises. One, with just a matrix element which has to be evaluated by calculating the integral, or in terms of this anti-symmetrized matrix element. So you can rewrite this as a sum over 1 over 4, and then you have an alpha, beta, gamma, delta, and then you can just add the same matrix element twice, gamma, delta, plus alpha, beta, v, gamma, delta. And this is multiplied with a alpha dagger, a beta dagger, a delta, and a gamma. Now, what I could do now is actually, when I look at the second term here, I can now rewrite that one in terms of the following. So I can have actually 1 over 4, and then I have an alpha, beta, gamma, delta, and then I have the matrix element alpha, beta, v, gamma, delta, and then I have my a dagger, a alpha, a gamma. But then what I could do now is just to use the anti-commutation rules and just rewrite that one as a minus 104 alpha, beta, gamma, delta, and then I have an alpha, beta, v, gamma, delta, and now I just interchanged the last two annihilation operators. So this is an alpha, gamma, and alpha, beta. Okay, alpha, delta here. Then in the last term, what I do now is I just interchange, these are just dummy variables, gamma, delta. In that specific case, what I get now is that I will have a delta gamma here, and then I get a delta gamma there. And if I collect the two terms, I get 1 over 4. So this is going to be, this term here is going to be the same as the one you have here when I interchange them. So I have an alpha, beta, gamma, delta. But then I have a matrix element which is different. So V of gamma, delta, minus alpha, beta of V delta gamma. And this is multiplied with A alpha, A beta, A delta, A gamma. And this matrix element which you see here is what we defined as the anti-symmetrized matrix element. Now this is going to simplify calculations, because if you keep these two contributions, so this term comes from the anti-symmetry of the wave function. If you want to calculate both, you do actually extra labor, because you would need to calculate the expectation values, including two matrix elements. But if you pre-calculate the anti-symmetrized matrix element, then you end up having to calculate just one contribution, because then you have pre-calculated the anti-symmetry. So you have a table of anti-symmetrized matrix elements, and you would just look them up, and this matrix element contains both these terms. And this is multiplied with A alpha dagger, A beta dagger, A delta, and A gamma. This is extremely useful if you're dealing with identical particles. If you have distinguishable particles, like if you're dealing with protons and neutrons, then you have to be a little bit more careful, but you can still redefine these matrix elements. So it's very useful when you're dealing with identical particles, like electrons, for instance. Now, what I want to do now is actually to motivate for Wick's theorem. So we saw now from the different calculations that it gets pretty boring and it's easy to make errors with indices when we are dealing with all these anti-commutators, where we shift the creation and operators creation to the left and annihilation to the right. So let's now look at Wick's theorem and how we can simplify these calculations here. So one of the first things we need now are some definitions. And I'm going to define the expected value, or the expectation here, in terms of two terms. So the basic one with an annihilation and creation operator. If we now look at this specific term here, which we have as an A alpha, A beta dagger acting on 0, this is something which we, in case they are the same, gives us a Kronecker delta. And this is again the same as if we write alpha or beta here. I also want to remind you of, if I now have A alpha, A beta acting on 0, this is the same as 0, A alpha dagger, A beta dagger acting on 0, and that's also equal to 0 of A alpha dagger, A beta of 0, and this is equal to 0. So there's only one term here which gives us a non-zero result. So let's take a closer look at how we can rewrite that specific term. So the way we actually did this was to implement the anti-commutation rules. So if we look at this specific term here, we can now rewrite it in terms of the anti-commutators, A beta dagger 0, and this is the same as 0, and then I have my delta alpha beta 0 minus of A beta of A alpha of 0. The last term is 0, right? But what I'm going to do now is to rewrite this in a different way. So I'm going to introduce a notation here, which we are going to use for the rest of the course. So I'm going to write this in terms of A alpha as a more compact way, dagger, and I'm going to put this term above here. So this is going to be called a contraction. So I contract alpha with beta, and that gives me 1 in case alpha is equal to beta. So this is called a contraction. And then I'm going to put a plus sign, plus here. And then I'm going to define something which I call a normal order product. And this is going to be the normal order product of A alpha, A beta dagger. And in our case, this is identical, this term is identical to minus 0 of A beta dagger, A alpha of 0. And this term which you see here is going to read A alpha, A beta of 0. Okay? So if I try A alpha, A beta dagger, this is obviously equal to 0. If I try A alpha dagger, A beta dagger, this is also equal to 0. And that follows from what we put here, these relations which you see here. And this is also equal to A alpha, A beta. Now, what does normal ordering mean? Now, normal ordering means that I reorder the creation and annihilation operators. So the creation operators are always to the left and the annihilation operators to the right. And then, depending on how many times I shift the order of these operators, so like if you look at this specific case here, I shift them once. So in order to get this normal ordered here, so this is normal ordered now, so I have a creation operator to the left and an annihilation operator to the right. And we know that 0 of A alpha dagger is equal to 0. And we know that A alpha acting on 0 is by definition equal to 0. Okay? And you see that there is a minus sign here. And the minus sign comes because I started with this expression here. That's where I started, here. And this expression here, in order to bring this into normal ordered form, that means that I have to switch alpha beta, A beta and A alpha, and that gives me a minus sign. So for every time I interchange a creation and annihilation operator, I get a minus sign. So the normal ordering, if we want to define that more general, so the normal ordering of a chain of operators. If I now take this chain of operators, suppose now x, y, without specifying them, z up to a w. So this is going to be, oops, just let me switch this off here. Let me just put, so this normal ordering here of this chain of operators is now given as a minus 1 up to p, where p is the number of permutations I'm making. So this is the creation operators. And multiplied with the chain of annihilation operators. So normal ordering means simply that we put all the creation operators to the left and annihilation to the right. And then when we act on the vacuum state, this gives automatically 0. So these are just definitions. And here we have the definition when we have 2 operators. Let's now look at the case when we have 3 operators. And let's just pick an example.
Can I just make a question really quickly?
Say again?
Can I just make a question?
Yeah, go ahead.
Can you go up a little bit when you
Yep.
were talking about the contractor? Yeah, here, when you wrote A alpha dagger,
Yep.
A beta, you
Yep.
wrote a contractor, right?
Yep.
But on the following ones, you didn't write the should there be, yeah. Is it the same thing?
Yeah.
Or? Oh, okay.
Yeah. I just forgot to put the contraction sign.
Okay.
So these contractions are automatically 0. And the only one which gives non-zero is the case when we have a creation operator which acts on the vacuum state. Later, we are going to redefine this when we introduce a Fermi level for fermions. And then we are going to have the so-called particle operators and hole operators. And then since we redefine the vacuum, then we have to be a little bit more careful. And what we will see then is that this relation here may actually be fulfilled if you have states below the Fermi level which are filled, because then the operator would act on a state which exists in your vacuum state. So you can always redefine your vacuum state. Now, the definitions we are using is that the vacuum state contains nothing. Okay, so let's now look at an example. We looked at this with 2 operators, one creation and one annihilation. If I have 2 operators of the same type, in this case, it's automatically 0. So the next case we need to look at is the case with 3 operators. And you can easily convince yourself that with 3 operators, an odd number of operators, whether these are creation or annihilations, it will always be 0. So the only terms which will give something which is different from 0 is if we have an even number of creation and annihilation operators. These will be the only cases which will be non-zero. So if somebody gives you an operator which has an odd number of creation and annihilation operators, that will automatically give 0 expectation values. But let's now look at the case which we have, and I'm just going to put some simple labels here, A1, A2, and A3. Now, if I now use my standard ways of ordering it, So I want to use this and let it act on a state, on the vacuum state. And because I'm going to use this to calculate an expectation value or transition probability. So what I do first now is actually to go through this boring exercise, which we did before. And then we are going to recognize the terms now as sets of contractions and normal ordering. So let's just rewrite it. And now we are going to reshuffle the creation operators to the left and annihilation to the right. Okay, that's the first step. So, and then the next, so if I write it out, this is going to be A1 delta 2 free minus, and then I'm going to change A1 with A3. So I'm going to have a delta 1 free minus a free dagger A1 of A2. And if I collect everything, I'm going to have three terms now. So on A1, that's the operator, delta 2 free minus, and then I have a delta 1 free, and A2 plus an A3 of A1 and A2 here. Okay, let's take a closer look at what we have and how we can actually rewrite it. Everything you see here, if I now take an expectation value from vacuum to vacuum, this is 0. There's no way that we can get something different from 0. So when you have an odd number of operators, this is always going to give you, for a vacuum to vacuum expectation value, it's always going to give you 0. Now let's take a look and use these definitions which we had. If we look at the first term, so this delta 2 free, this is actually A2, A3 dagger. This is the contraction which we had. So the Kronecker delta is a contraction. Now A1 here means that we have taken, if we take this one, we can rewrite this term here as a normal order product of the operators A1, A2, A3 dagger with a contraction here. Okay? Does that sound? If we use these definitions of contractions and normal ordering, which we put up, the next term, and now I'm just going to write this with a plus because I have to find all the relevant contractions. So if I look at the next one, so I have a contraction with A1 and A3. Now, in order for these to be calculated, I have to interchange A2 with A1. That gives rise to a minus sign, which is the one we see here. Then, so that's this term, written in a more abstract way. And then we take the next term. If we look at that one, we can rewrite that one as an N, and we keep this ordering because this is the ordering we started with. And that ordering may reflect the way we have ordered the single particle energies. Now, if you look at what you have here, this is no contractions because we have all the free operators, but this is actually the normal ordered way of setting up this operator here with contraction to the, with the creation to the right, not to the left, and annihilation to the right. So then what I do now, I flip A3 with A2 once, and then I have A3 with A1. So the first thing I do now when I want to normal order it and to get this form, which is going to give me 0. So normal ordering means that all the creations operators are to the left and annihilation to the right. And this one, when we act on 0, when it takes 0 here, that gives 0. So what you see now, I first interchange this, a minus sign, and then I interchange that one, another minus sign. So I do 2 times, and if I go back to the definition, I have 2 times here, and then I have the final expression. So this is a more compact way of writing it. So what you see now is I have the normal order product of the operators, and then the sum over the possible contractions between 2 operators. So now we are getting a little bit ambitious. So let's take 4 operators. And then you will start to see a given pattern here. So let me go through that example, because then we can actually rewrite that in terms of all possible contractions, one possible contraction, and a final normal order product. So let's do the next example. And then from that one, we can then see what Wick's theorem is going to look like. So we're going to show it for two operators, 3 operators, and 4 operators by just going through every things in glory details. Then Wick's theorem is shown by induction. If you add a new operator, you can then prove that the form which we found for 2, 3, and 4 can be extended to 5, to 6, and so on. So the theorem itself is proven by induction. But let's now look at the case where we now want to calculate a series of 4 operators, and we have 2 creation and 2 annihilation operators. If we'd had only annihilation operators, this would have been 0. If I had only creation operators, it would be 0. If I had 3 creation operators and 1 annihilation operator, it would be 0, and so on. So that's pretty easy to see that you need this specific combination here. And by the way, this window can actually not be closed. Really? No, it cannot. Because there's no handle there. So when winter comes, this is going to be fun. Eh? I was getting this breezy, and it's always a little bit irritating. Yeah. Okay. So let's now just start the massaging of this equation here. So we just skip the zeros, and we just write out the different terms. So if we take the first term here, what we are going to get. So we're going to get now an A1, A2. So what I'm going to do now is to shuffle everything so I get the creation operators to the left and the annihilation operators to the right. So I'm taking 2 and 3 and use the anti-commutation relations there. So I have an A dagger, A2, and A4 dagger. So that's the first thing I do. Now I take these 2 guys here and I anti-commute them. Then my next step now, sorry, this should not be an A1, A2 here. This should not be there. It's just an A1 acting on that expression. Then, so my next term is now an A1 multiplied with an A4 dagger of delta 2, 3. And then I get a minus an A1, an A3 dagger, an A2, and an A4 dagger. So I just keep massaging here. I get minus, and now I'm taking A1 and A3 here. That gives me a Kronecker delta, A1, 3, minus A3 dagger, A1. And then I have this multiplied with A2 and A4 dagger. Okay? So it's not very exciting here. Huh? Then I can reshuffle everything. So what I'm going to get now is an A1, A4 dagger, delta 2, 3, minus delta 1, 3, A2, A4 dagger, plus, and then I have this A3 dagger, A1, A2, and A4 dagger, like this. And I can rewrite this now when we do the full exercise. So I'm just going to reshuffle everything. So at the end, you have the creation to the left and annihilation to the right. So when I repeat these exercises here and here and with these ones, I'm going to sum up now and going to set up the final answer. So I get a delta 2, 3, a delta 1, 4, minus a delta 2, 3 of A4 dagger, A1, minus a delta 1, 3 of delta 2, 4, plus, and then I have a delta 1, 3 of A4 dagger of A2. So let me see if I have everything here, plus a delta 2, 4 of A3 dagger A1 minus an A3 dagger A2 of delta 4, 1. And then I have the final term, which is an A3 dagger, an A4 dagger of A1, A2. So this is if I just went through this in a very slavish manner. So as you see now, there are only two terms which survive here, right? This is gives different from zero, and this is different from zero. All the rest, when they act on a vacuum state, give zero. So can we generalize this? So let's take a look now. So let's look at the terms. So the first term here is something which we now can write in terms of the operator which we had, n, and then we had A1, A2, A3 dagger, A4 dagger. So this is two contractions. So is this contracted with A3, which gives us that Kronecker delta, and then this contracted with that. Okay? If I look at the next one, and now I'm just writing the pluses here without thinking of the specific minus signs, but they will come out when we do the contractions. And then I had an A4 dagger. So in this specific case, what I have is still this Kronecker delta. So I perform that one. That gives me the Kronecker delta, the contraction. And then I have A1, A3, and I want to normal order that one. And that means that I have to shuffle A4 to the right, to the left, and A1 to the right, and that gives me a minus sign. If I take the next one, this is going to be again A1, A2, A3, and A4. So in this particular case, I've performed this contraction. So as you can see here, I'm looking at all contractions which give something different from zero. So in this calculation here, we are excluding AI, AJ, this type. This is excluded because that gives automatically zero, and you will never have a Kronecker delta there. So in the equation which we are setting up, in principle, you could think of summing over all possibilities. This is automatically zero. This is zero. And similarly, if I have AI, AJ, this is also zero. So they will not show up in this expression which we got by using the anti-commutation rules. So if we now look at this, the next term which we have, the fourth term, so that would be given by n, and then I have again A1, A2, A3, A4. Yeah.
Isn't that number delta 2, 4 usually the previous one?
So let me see now. So you have a, so I have a, I've taken this one. Oh, sorry. Sorry, yeah, I have to go. I actually forgot that one. Thanks. So the, you're right, because I was a little bit too hasty. I actually forgot this term. So I have a 1, 3, and then I have a 2, 4. Thanks. Then I have the next term, which is this one. So this is as always what happens when you have your notes in front of you, and then you just read the wrong line. Okay, so the next one, which you see here, is a delta 1, 3. So we have this specific contraction like that, and then we have the normal ordering of A4 and A2. So in order to bring these two operators, A1 and A3, close to each other, we have to flip A2. That gives a minus sign, and then we flip A4 and A2, so that gives a plus sign. And then we are back to the right expression. So let's take the next term. So that's an N, and then we have an A1, A2, A3, and A4 dagger. So you see the next one has a contraction with delta 2 and with A2 and 4. So in this specific case, I need to change A3 with A4, gives me a minus sign, and then I flip A1 and A3 to get the normal ordered form, which we have here, and that gives you a minus sign, so that gives a plus. Then I have plus, a normal ordered, and then I have A1, A2, A3, and A4. And in that particular case, what I have is a delta 4, 1, this one. And again, if you do the write interchanges, you get the minus sign. And finally, what we have is just a term where we take the operator and simply interchange everything so that we have just a normal order product. So this final term which you see here, this term here, is the same as the one which we see here. So we change A4 here, minus, in here, another minus, and over here, another minus. And then we do the same thing with this one, with A3 and A1 and A2, and then we get the right sign, which is a plus, when we've done all the permutations. Okay? So we do this one, 1, 2, plus, and then we have changed 3, so then we need this one with that one, minus, this one with that one, plus. Now, if you now look at what we have, and you make a comparison with what we did with the free body, with the free operators, so we got one term here, which contained the just straight normal order product, and then a sum of all the possible contractions which we could have, which are non-zero. The non-zero contractions, keep that in mind. Because if I take this one, that's 0. If I take that one, it's 0. So it's only the non-zero contractions. You can obviously sum freely of all of them if you want to. But if we want to systematize this, you can now rewrite this as normal order product of A1, A2, A3 dagger, A4 dagger, plus, and now I'm going to introduce a notation here where this 1 means that they have a pair of annihilation and creation operators. So I sum over all the possible contractions I can make with a creation and annihilation operator, but just one contraction. So this is one contraction. And now I have A1, A2, A3, A4 dagger, like this. And now I'm just indicating that I only have one contraction. So it's the sum of all the 1 possibilities. And then I have a final term where I have 2 contractions. And you see why you need pairs of operators here. And I'm just indicating this with these signs here. So this term which you see here, this term here, is actually what we had here and here. The 1 contraction guys are all these guys here. 1 contraction. And you see that I've looked at all the possibilities now, which can be made. And finally, you have the final normal order product. Now, this can now be generalized to chains of operators. So what it means is if I'm calculating the expectation value now, and this is Wick's theorem, this is now going to be given. So this is a chain of operators being applied to a vacuum state. So this will contain the normal order product plus the sum over 1 contraction, and I write it in this kind of strange notation here. And this is where we're going to stop today. So I write this one like that, plus the sum over 2 contractions. And this is actually Wick's theorem, which you're seeing now. And tomorrow we're going to prove it. So we have 2 contractions. And finally, this goes through all the pairs of contractions till we have the final one. And this n is a number of operators divided by 2. And then I have n of x, y, z up to w. And I'm marking this like this. So all the operators are now contracted in one way or the other one. And this is Wick's theorem. So what we have done is to show it for 2, 3, and 4 operators. What we are going to prove tomorrow is the generalization to n operators. And this is going to be done by induction. This is a standard way to prove Wick's theorem. Now, if you look at this expression here, you see now that there is only one term which survives, which gives something which is non-zero. And that's the last term. All the other terms will now involve a set of annihilation operators acting to the left, to the right. And that will always give us something which is zero. So if you go back to the 4-operator case, you see now that when I act on the vacuum state with this one, gives 0, this gives 0, 0, 0, and 0. And the only terms which survive are this one and that one. And this is written in a compact way in terms of just this single term here. And that simplifies life. So when we are calculating expectation values or transition probabilities, we only need to look at the last term and just have the sum of all the possible contractions. And that's the strength. That's going to simplify the way we calculate things. And I'm going to stop the recording. And this